All right. Hello, everyone. Please join me in welcoming Amjith Ramanujam, talking about how Netflix does failovers in 7 minutes flat.
Thank you. Netflix is one of those services that evokes very strong emotional response from our, from our customers. People follow our shows very passionately. Let's see why that is.
Stay away from me. Stay away from my clients.
No. You're a ticking time bomb.
Keep telling me who I am. How dare
Maybe
you?
you blame your family for getting killed in an accident.
As I was saying, very strong emotional response. Sometimes it's a mild inconvenience, and other times it's absolute rage when that happens. I'm part of an organization at Netflix called the Cloud Production Engineering, and our job is to make sure that you never have to see that screen. My name is Amjith. I'm part of the traffic team at Netflix, and we do regional failovers. And I'm here to talk to you about how we do regional failovers and how we manage to get it under 7 minutes. Failover is a concept that is most familiar in the database field, where you have a primary and a secondary, and when the primary goes down, the secondary, you do a failover to the secondary, and the secondary takes over. And this can be generalized to any computer system, where the standby system takes over when the main system fails. And a regional failover, it simply means that your standby system is in a different region. What I mean by that is that it is in a different data center and perhaps in a different geographical location. And this is a good time to tell you that Netflix does not own their own data centers. We do not own any server racks. We run almost entirely in AWS. All the interactions that you do on the website, the searching, the thumbs up, all of the viewing of the rows of shows, all of those are served by services that are running in AWS instances. Right when you press play, it starts to make sure that the license is good, and after that, the video file itself comes from a internal CDN that we have built called Netflix Open Connect. So apart from that, we don't own any hardware. Everything is owned by AWS, and we happen to just rent it from them. And we run in 3 separate regions in AWS, one in US West, one in US East, and one in European data center called EU West. And we have reserved enough capacity in all 3 regions so that if any one of these regions were to go down, the other 2 can absorb all of the traffic from that one region that has just gone down. Why did we do that? Well, the story goes back to Christmas Eve of 2012. There was a light dusting of snow on the ground, and families were gathered around the fireplace, chestnuts were roasting. At the same time, across the country, a war room was being assembled in a town called Los Gatos. That's where Netflix's headquarters is located. Half a dozen engineers were gathered into the war room trying to figure out why Netflix wasn't working. After much finger pointing and staring at the charts, we figured out that it was actually because there was an ELB outage. ELBs are a service that are provided by AWS. It stands for Elastic Load Balancer. These are the frontline services that receive the traffic from the internet and then pass them down to the servers that are running the different services. And this ELB outage happened to be was in US East, which was where most of Netflix was running at the time. And this lasted for about 7 hours. To tell you why this is bad, every single day, people watch about 16,000 years worth of Netflix video. So when we were out for 7 hours, we robbed humanity of 4,600 years of entertainment. So we vowed to never, ever put people through this kind of absolute misery. And so we started investing in regional failovers. But before we could just simply go out and do the regional failovers, we needed a couple of prerequisites. We had hundreds and hundreds of microservices running in our ecosystem, and we wanted to make sure that these services were stateless. And what I mean by that is if I move a service from one of the servers to a different server, or perhaps from one data center to a different data center, it should just continue to work. It should not have state that is stored on the machine that it requires. And this was a fairly straightforward thing, because by this time, we were already running Chaos Monkey in production. And if you are not aware of Chaos Monkey, in Netflix, we have a service called Chaos Monkey that goes out and kills instances in production. And we do this to ensure that all of our services have resiliency built in, and they have fallbacks built in, so that taking out one server from a service does not bring down the service completely. So the services were already sort of stateless, and we wanted to make sure that it was pretty good. And so this is one of the prerequisites. The other prerequisite is that we wanted the data that these services were fetching from or writing to are regionally replicated. So we wanted them in all of our data centers, copies of these things duplicated in all of the data centers. We use Cassandra for that, and we have a small team of engineers who make sure and maintain the Cassandra clusters and fine-tune them and make sure they're all regionally replicated. So all the data is available in all the data centers. Once these two prerequisites were satisfied, we started defining what are some good problems that a failover can actually solve. One, which is the obvious one, which is if you have an infrastructure problem, let's say there was a network partition in AWS, or if a undersea cable was cut by sharks biting it or something, that would be a good scenario where we could evacuate, because one region will be affected by that, and we move all the traffic from that region, and we'll be good to go. The other one is we wanted to confirm that a problem that is happening is not widespread. It is isolated to one region, but at the same time, if I move the traffic from that region to the next region, it doesn't follow. What would be a good example is if, for some reason, somebody is DDoSing Netflix, and it happens to be isolated to US East 1, we decide to move the traffic to US West 2 and EU, we've just made the problem much worse, because now the DDoS is happening on two data centers. So that is not a good candidate. But if it is not, if the problem won't move with the traffic, then that is a good candidate as well. And as I mentioned briefly before, we run on hundreds of microservices. And so we do thousands of production changes on a single day. There are deploys going on. There are configuration changes that are being changed. And so there is a really good chance that we shoot ourselves in the foot multiple times a day. And so if a bad deploy does go out and it is severe enough that an entire region is being affected, then we immediately fail over. That is also a good candidate where we could fail over, and then we could try to root cause the problem. So these are all good candidates. So what does the actual failover itself look like? Well, a regional failover process is quite straightforward. First, we detect the problem. We scale the savior regions, and then we shift traffic. How hard could it be? Well, let's go into each step and try to define a little bit more in detail. So detecting the problem. You might think that it is as simple as just loading up Netflix and seeing if the video plays or not. But we work in smart TVs, PS3, your browser, mobile phones, and Xboxes, all of these different devices. It could not be working in any one of these devices, and that is still considered an outage. So that is not a good way. And we also run in 160, we're also available in 160 different countries. So even if it works in the US, it does not guarantee that it's working in Brazil or in Japan. So we needed a way to find out for sure that we are actually having a problem. We needed one metric to rule them all, as the wise wizard Dumbledore said. We do have one of those metrics. It's called SPS, which stands for stream starts per second. What this means is how many streams were successfully started in 1 second. And we keep this metric isolated for each region. We have it partitioned for each region. And we track this week over week. And we can try to find out if the current SPS seems to be dipping below last week's number or yesterday's number, then there is probably a problem that is going on. And if this is happening only in one region, then there is a good chance that a failover could save this problem. So that is the metric that we use. And scaling the saviors. As I mentioned before, we have hundreds of microservices that are running concurrently. And they all take different types of traffic. It is not simply, the SPS does not track with how much work is done by each of these services. So it's hard to determine how to scale hundreds of these clusters appropriately in order to just shift the traffic. So how do we know how to scale these individual clusters? What is a good number to scale them to? And also, in addition to that, you notice that the SPS is actually diurnal. It has a pattern. We have peak times, which are from 5 p.m. to 10 p.m., and there are off-peak times, which are at 3 a.m. or some other hour. And this, again, since we run in different regions of the world, the 5 p.m. comes around at different times. In the East Coast, it comes around at 5 p.m. West Coast, it's 3 hours later. And in Europe, it comes at some ungodly hour. So we don't know exactly what is the demand that is being served in each of these clusters. We do, but in order to actually shift the traffic, there is a little bit more going on here that is a little bit complex. So we need to figure out how to scale these different clusters for that time of day. So we just wing it. Totally kidding. So in addition to actually keeping track of the stream starts per second, we also monitor the cluster sizes of the various clusters of all the hundreds of services that we run. And we keep track of this data in our internal monitoring tool called Atlas. And that is an open source tool that has been released by Netflix. So if you're interested, check them out. And you'll notice that the scaling pattern of these clusters also goes up and down. And we use Amazon's auto-scaling rules in order to do this based on the traffic that we receive, based on the CPU utilization of the different services, and so on. And so if we can plot the scaling patterns against the demand that we see in that region, then we can easily identify what is the efficiency of a single instance for that particular service that it can handle in terms of relating the SPS to the utilization. And we use linear regression to figure out to actually just predict what is it that is needed at this time of day in order to handle the amount of traffic that I'm going to divert into that cluster. Once we have that and we have successfully scaled that cluster, we shift the traffic, which is a two-step process. We have something called as an edge proxy. And this edge proxy is a service that receives the traffic from the users, and it does a bunch of things like load shedding, and it does retries, and one of the features that it does is it can do regional proxying, meaning we can tell this edge proxy that divert 10% of the traffic that's coming into this region into the other two regions, and it can incrementally divert some of this region and some of the traffic. We use that to make sure that our scaling numbers are actually accurate, and we can actually scale the other regions appropriately based on the traffic. And once we are confident that we have scaled them appropriately, we simply switch DNS and make that region disappear, and all the traffic will then go to the other two regions. This is how a failover looks like. The central circle that you see is the internet that's sending traffic, and the three circles on the edges are the three data centers that we have, the three regions. In the beginning, they all receive almost equal traffic. As soon as we detect a problem, we start proxying some of the traffic, and once we have some confidence that the proxying is working accurately, we simply cut over the DNS and make the third region disappear completely. So let's tally up how long it takes. Detecting the problem, this is not really part of the failover, but that takes about 5 minutes. Scaling the savior regions, it takes about 35 minutes. And shifting traffic, including the incremental proxying and the DNS cutover, takes about 10 minutes. So a total of 45 minutes. You're probably wondering why the hell I named the title as 7 minutes. So this is completely unacceptable. We can't be taking 45 minutes to fail over a region, because that is one full episode of Jessica Jones that you could have finished. So we decided to do the next iteration of this regional failover. We called it Nimble, and one explicit goal is our failovers must happen under 10 minutes. So it should be a single-digit minute that we should finish this in. And secondary goal, which was it should be completely transparent to the service owners. So we did not want to put the burden on the service owners to make code changes to accommodate this new type of failover, and we also did not want them to add more operational overhead for them by telling them to modify their auto-scaling policies or any of the other typical operational behavior that they use to operate their services. So I'm going to explain how Nimble works. let's say that this is one of the regions, US West, and I've chosen randomly a representative cluster here. The boxes are the clusters in which that service is running, and the little donuts are the actual instances that are in that box. What we did was we created a shadow cluster that matches exactly what the live cluster, which is serving the traffic, does. We just simply named it Nimble underscore and then the actual service name. And in order to determine how many instances to throw into that shadow cluster, remember how I told you that we use a linear regression at the time of failover to predict how much to scale those savior regions. Instead of running that algorithm only at the time of failover, we decided to run it every 5 minutes. And we take the output that comes from that, and we use a service to stock by topping up the shadow clusters or bringing it down if we're going into an off-peak time. So we are constantly maintaining the number of instances there in the shadow cluster. And these shadow clusters are not taking traffic because inside of Netflix, every instance is supposed to start up, run through a bunch of startup checks, and then they're supposed to register themselves with Discovery Service. Once they register themselves with Discovery Service, that means they're ready to take traffic. We made a small tweak to that client which does this process to say, if you happen to be a Nimble instance, don't register yourself with the Discovery Service, and we simply put a gate there. Unless we remove that gate, it cannot move forward. So that's how we make sure that these instances are not polluting by taking up the traffic and messing with the operational metrics that a service owner would normally see in their regular operation. At the time of failover, what we do is we are now ready to move traffic. So we remove the gate, and so they become available and they're ready to take traffic. We shift the traffic, and while the traffic is being served by the Nimble instances, we slowly transplant them from the shadow cluster into the live cluster. So we pluck them out of the shadow cluster, and then we put them into the live cluster. Now the live cluster looks like it has instantaneously scaled up by X number of instances that is appropriate for that given time of the day. So that is Nimble in a nutshell, how we do Nimble with the new one. And now, if we take a tally, scaling the savior region is simply plucking instances from a shadow cluster and putting them into the live cluster. And that takes about 4 minutes for all hundreds of clusters that we manage. And shifting traffic, we're not incrementally shifting traffic anymore because we are previously scaling took about 35 minutes. And we know that in 35 minutes, the predictions would have fallen out of date. And so we needed the proxying in order to slowly send some traffic and make sure that if we are off in the prediction, we can top them up. But now, since the scaling happens in under 4 minutes, we know that our predictions are fairly accurate. And so we simply cut over the DNS, and we just skip over the proxying step. And DNS propagation takes about 3 minutes. And so at the end of it, it's only about 7 minutes where we are completely evacuated from a region. And you'll also notice that detecting the problem now only takes 2 minutes. The reason is because previously, when a failover takes about 45 minutes, people tend to not just detect the problem, but they try to root cause, and they're trying to find out, like, is there an easy solution with which I could fix this problem? But now, let's failover first. It takes 7 minutes. How hard could it be? And then we can root cause the problem later. And so it's a bit of a behavior change that has happened, and we noticed that it only takes 2 minutes for people to call the failover or pull the trigger, if you will. So how does this all work, and why is this presented at PyCon? And so all of the Nimble, all this orchestration is all written using Python. And our architecture has 2 separate types of tasks that we do. One is periodic tasks, and the other is a triggered task at the time of failover. And the periodic tasks are fetching historical data. So we do this from our internal monitoring system. We do this every 5 or 10 minutes. And there is another service that simply takes the historical data, and then when I say historical data, I'm talking about 2 weeks worth of data. It's not much more than that. And then we use the 2 weeks worth of data, and we try to predict how the cluster size is if we were to do a failover at that given second. And then there is a third service that takes those scaling numbers, and then it says, I'm going to bump up the dark cluster sizes every 5 minutes. And the triggered tasks are the ones that are triggered when we are ready to do a failover, when we are going to do a failover, which is ungating the dark instances and plucking them from the shadow cluster and putting them into the live cluster, and actually cutting the DNS over, and so we can shift the traffic completely. So these are the trigger tasks that I talked about. And these are all written as Python scripts. And I call them nano services because none of these scripts depend on another one to actually finish. They all run periodically, and if they check to see what the state is, and if they are supposed to be in a failover state, they will do the task that they are required to do. We use Python, Flask, and we use Redis for our cache, and we use RQ for asynchronous task workers. The reason I'm not going too much into this is because these are all very well-known, established technologies. We're using really boring technology here to make sure that our stuff is actually really stable, because when you are doing a failover, there is a very good chance that things are on fire. You need something that is very dependable and stable, and Python has helped us out quite a bit in that area. It's very well established, and it's one of the stable technologies. Some of the characteristics of the services that we've built is, one of them is anticipating failure. Everybody says that, of course, I write defensive code. I check the inputs that come in, and I make sure that my outputs are clean and all that. And that is true. But what I'm talking about in terms of anticipating failure is we need fallbacks for everything. When I'm trying to fetch the historic data, my monitoring system could be down, because if an entire region is out, there is a very good chance our internal monitoring system is down. Or if I try to read to make sure that AWS state is up to date, the service that caches that data locally, that could also be out. So some of the characteristics are, we make sure that we write software that anticipates failure in every single one of the calls that we make. And we write it in a manner where we have to anticipate that it is an eventually consistent system, because AWS does not simply magically scale. When we say scale this by 10 instances, it is not instantaneous. It'll eventually get there to the 10 instances. And when we are working in the scale of tens of thousands of instances in each region, and put together it's hundreds of thousands of instances that we are moving at any given failover, things will go wrong, and there will be instances that will be left out and it's missed in our account keeping. And so we have a garbage collector that comes in and reaps instances that are not part of clusters. Anticipating failure, so we run this Nimble service in all 3 regions. They do primary election by leader election to make sure which one is going to actually do the failover. And every one of these that runs every 5 minutes, they will rebuild the state from scratch. We don't assume that the last iteration was successful. We rebuild the state from scratch. And for that, we have to read AWS state. And AWS will throttle the hell out of us if we keep doing this every 5 minutes. So we have an internal cache. And we build fallbacks for every one of them. I'm going to talk about the internal cache. So for AWS state, we have open sourced a project called EDA, which is an internal cache that you could use that keeps the current working state of all of your AWS services. And for historical data, we use Atlas. And Atlas, again, it is an open source project that we've open sourced, like Netflix has open source. And all the data that we pull from here, you will notice that these are already caches of things that are from the real world, like AWS. And all of this is stored locally in our cache, either in a Redis cache or as file system files. And so if we are not able to reach EDA service for one of the iterations, we will use a slightly outdated data from our local cache. So that's the fallback that I was talking about. And for eventual consistency, we know that AWS is eventually consistent, and so we favor idempotent actions. And what I mean by that is, it is an action that if you execute multiple times, the result won't change. It's like multiplying a number by 1. No matter how many times you multiply that number by 1, the result is going to be the same. To give you an actual example is, we don't ever say, increase this cluster size by 5. We always say, set the cluster size to 35, for example. So you can issue that command multiple times and make sure that it is not going to incrementally keep increasing over time. And the garbage cleaner that I talked about is, we call it the orphan cleaner. So it detects any instances that are not attached to any of the cluster. And some of the safety features we built into that is, we have to terminate instances slowly, meaning if you find out that there are 150 instances that are taking traffic that are not part of cluster, if you terminate all 50 of them, there is a good chance that the reactive scaling for the actual cluster is not going to immediately populate 50 instances because this was missing. So we do that slowly. And we also put in a circuit breaker, if you will, where it'll notice that if there are 100 instances that needs to be terminated, it'll simply say, I'm not going to touch this because there is probably something else going on, and it'll immediately page us. So one of us has to go in and make sure that those 100 instances are in fact orphans, or whether we could do something about it. So some of the questions that people typically ask are, how often do we actually have to do the failover? Well, we call this particular exercise as chaos Kong, because it is, instead of terminating a single instance like a chaos monkey, we're terminating an entire region, so it's chaos Kong. It's only fair. We call it that. And we do this more than once a month, just to exercise that it is still functioning, and also to make sure that services are still maintained as stateless services and they're not writing region-specific logic in them. So if we do a planned one during the day when everyone is fully awake, we can immediately identify what services are struggling, and we can immediately reach out to the service owner and ask them how to fix that on the fly. The other question that we usually get is, why not have the dark clusters actually take traffic? Why do they have to be just doing health checks and waiting? What is the problem there? The problem there is, if they start taking traffic, it is going to start impacting the auto-scaling policies of the live clusters. The live clusters have CPU utilization, or number of requests per second that they use in order to auto-scale. If the dark clusters start taking traffic, then that is going to impact the operational characteristics of the live cluster. You might wonder, what is wrong with that? Well, we lose the scaling pattern that goes up and down, and our linear regression will lose its validity pretty quickly in just a day, because we won't have the up and down scaling pattern. And so we won't know the efficiency of each instance. The next iteration of our Nimble might actually mean that we will actually squeeze test these services and find out what the efficiency of each individual instance is, and then we won't have to keep the dark clusters just health checking. We can just add them to the live cluster and have them go up and down. And the last question that I get is, how much did Nimble cost? It's actually cost neutral, because we already have these reserved instances that we have bought from Amazon that we're not using when we are going up and down and during our scaling pattern. And so we simply are just now using them, and they're just doing health checks, and they're technically, they do not add additional cost to us. If you are planning on doing failovers in your current job, my biggest suggestion is build fallbacks for your fallbacks, and make sure that also has fallbacks for it. And exercise this operation often, at least once a month, if not more. And provide visibility to your service owners that a failover is happening and their cluster sizes are going to increase, and so on. That helps a lot. If any of this sounds interesting to you, we have a job fair table. My name is Amjith, and I am on Twitter at AmjithR. My DMs are open. Reach out to me. I'll be happy to answer questions and find out if it is a good fit for you or not. If you have any other questions, feel free to ask me. Microphones are in the back. Thank you.
Does this work? Oh, OK. Hey, I have a question.
Yes.
So you illustrated how the importance of metrics to detect some of these outages. Once you evacuate a region, how do you know when it's a good time to start migrating back?
So a couple of things. One, if it is a problem on AWS's side, then they will actually let us know that the problem has been resolved. And when we restore, we actually take a more cautious approach of restoring and moving things incrementally to notice that it is actually resolved. The other thing is, if it was a bad deploy that has gone wrong, then we just give the service owners time to roll back their deploys, and then we restore, and then they get to try it again. So there is not a good metric for us to figure out if the problem in if the issue in the problematic region has gone away or not. It's mostly just humans telling us.
OK, thanks. And do you ever turn off Chaos Monkey during a disaster? Like, do you ever say,
yes.
let's, OK, just.
Yeah.
Okay.
The Chaos Monkey will stop killing instances when we are doing a Chaos Kong.
OK.
Yeah.
All right, thank you.
Yeah.
Hi, my name is Kumran. I have a question about the content. Do you do the replication of the content also, or just the programs and microservices?
Sorry, the application of the what type?
The content, like the video content and other features that is serviced. Do you replicate the data between the data centers?
Ah, I see. So the content itself does not come from AWS. They come from our CDNs, and our CDNs are completely separate. So after you have started a stream, the video files are coming from the CDN directly to your device, and at that point, AWS has nothing to do with it. And so the content is replicated in multiple CDNs, but it is not replicated in AWS infrastructure.
Thank you.
I have a question. In terms of code deployments and failures caused by those deployments, do you have any intelligent service or some solution in place that can, with a high success rate, determine whether a failure is tied to any code deployments and would automatically roll back?
No, we do not. So we have something called automatic canary analysis. So before a code gets deployed, they go through sort of an experimentation where a small cluster will be spun up with the new code, and the production traffic will actually go through the new code. And they have metrics that compare to make sure the old metrics and the new metrics are actually matching. So that's called canary analysis, and that is also an open source tool that Netflix has released that people have used to make sure the deploys are actually stable. If this one, we don't have any analysis afterwards. The afterwards analysis is mostly the service owners telling us that there is something wrong going on, or if there is an error metric that we actually follow, then the error metric will tell us that this is due to a deploy. And right now, this is a manual process. Somebody has to trigger a failover to start. In the future, there is a possibility that we could automate it. Yeah, but right now, it's all manual.
Sure.
Unfortunately, that's all the time we have for questions. But Amjith has said he'll take some questions in the hallway as well. Let's thank him again.
Thank you.